Greetings and welcome, friends. We were talking about an additional type of transformation yesterday called reflections. Whoa, I almost said the wrong one there. But don't worry, here we go. We're going over some of last night's quest. It says, which transformation does not belong with the other three? Oh, wow, accuser. You're just like, you don't belong. There was like a very dramatic pointing that happened here. Internet friends. But yeah, it looks like this would be a reflection over the y-axis. What is the equation for the y-axis, by the way? The equation of that vertical line. Oh, it's actually, yeah, it's x equals 0. It's kind of the opposite of what you might think. This one looks like a reflection over the x-axis, which is the equation y equals 0. This one looks like a reflection over the x-axis, and this one looks like it done be a translatin'. Yeah, so this one does not belong, which is probably what you guys noticed right away, yeah. What is the vector that translates this, by the way, in component form? Yep, no worries. No worries, good. So, determine whether the coordinate plane shows a reflection in the x-axis, y-axis, or neither. Well, based on those options, I think it's neither, yeah. I think it's neither. Is there a reflection that could describe this? That is actually true. More typically, it'd be called the y equals negative x. But yeah, it looks like it's reflected there. Could I have obtained this using a double reflection? If I reflected it over this, and then over this, almost, right? But yeah, it would have been pointing. Actually, that's interesting. This double reflection also could be described as a rotation, which we'll be talking about today. Yeah. So this one's neither of those, but yeah, it was the y equals negative x. All right, graph the polygon and its image over the line y equals negative x. It's my favorite line for reflecting time. Ooh, wrong color. Oops. Got to click on my inkwell there. All right, so for my reflection, we reflect perpendicular to the line of reflection and equidistant on the opposite side. So point A is half a diagonal away, so half a diagonal away over here is going to be A prime. D appears to be 1, 2, and 1/2 diagonal, so 1, a half, and then 2 for the D prime. C was 2 diagonals, so 2 diagonals this way would be C prime. And B was on the line, so B prime and B are one and the same. It got mapped onto itself there. Let's see. Oh, I'm actually... we did end up getting a list of some properties for reflections where you could like opposite the x or y coordinate. You could change the x and y coordinates. I don't have those ones memorized myself, but it is in our packet. But yeah, there is another way to think about it using it coordinately. But since this was given as a graph, I think the idea of working perpendicular and equidistant is the easier way to, right? So that's the idea, is that the image and the pre-image are equidistant and perpendicular to the line there. Ooh, yeah, you guys are welcome that I pre-graphed the pre-image for you. So here it says we're doing, looks like a compound transformation. So we're going to translate to, right, add 2, so t is going to be right 2 up 2 to t prime. S is going to be over 2 up 2 for S prime, and R is going to be over 2 up 2 for S prime, T prime, R prime. Man, I'm practicing my letters, as you guys can tell. And then a reflection in the line y equals x. Does anyone remember what those properties were? If I did want to opposite coordinates, I guess I could have done this all coordinately. But here's the line y equals x, the classic diagonal. The x and the y get swapped. Okay, so we'll do this for t prime anyway. So t prime looks like it was at 8, 6. So if I go to 6, 8, that should be t double prime. And it is, in fact. And notice in terms of reflection, one diagonal and one diagonal away, that it does land in the right spot. So yeah, so R was at 6, 3. So if I go to 3, 6, that should be R double prime. R double prime. And yeah, that was 1.5 diagonals, 1.5 diagonals. And S was at 9, 5, so at 5, 9 should be S double prime. And yeah, so this would be my final result from that compound transformation. And the combining multiple rigid transformations results in a rigid transformation, meaning even though these two, even though it got flipped and shifted, that the corresponding parts are still going to be congruent to one another. All right. And by that, I mean both their corresponding sides and their corresponding angles. All right. So, yeah, now my sketch is just getting all scratched up here, but that's fine. Bam, you get the idea. All right, last one, I think. Oh, determine the number of lines of symmetry. This would actually be a really interesting question for today's lesson, but linear symmetry also works. Actually, I won't use my ruler tool. So it looks like I could mirror this over itself. Right, yeah, you guys, I know. But you can think about it right now. So that's one. I think I can hit this one. And this one. So I think it's just 3. Did I miss one? Oh, I missed this one, yeah. Oh man, I'm terrible. Yeah, it should be 5. Yeah. Classic. Yeah. So yeah, you got to go from like point to armpit for this one, which armpit stars, you know, you never probably thought about them that way. Actually, how many armpits does a starfish have? That's an interesting thought. But I'll leave that for the internet to answer. Have a great day, friends.